So in this related rates video, we have water flowing into a tank in the form of an inverted cone having an altitude of 16 meters and a radius of 4 meters. The water is flowing into this inverted cone at a rate of 2 meters cubed per minute. This is volume units, so that's why it's meters cubed. And I want to know how fast is the radius changing at the instant that the radius in the tank is 2.5 meters. Okay, I know that's kind of a lot to digest, but number one is always the same. What do they want? So I see where it says find or what or how fast. That is typically talking about a derivative. How fast is the radius changing? So it's changing with respect to time, with respect to minutes. So I'm looking for dr dt, the derivative of the radius with respect to time and minutes. Now, number two, I need to write down everything that I know. First thing I'm going to do is draw a picture of an inverted cone. So what's an inverted cone look like? This is a cone, kind of like an ice cream cone, right? And so this thing is getting filled up with water, and we've got a radius. Now, the height, h, this altitude here is 16 meters, we're told, and the radius r is 4 meters in total. Okay, so I've got my picture. Now I want to write down what I know. I know that I'm looking for how fast the radius is changing at the instant where the water in the tank has a radius of 2.5 meters. So since it's less than the 4 meter radius, I know that the water isn't all the way up to the top yet. As the water level increases, so does the radius. The radius gets larger. So I also know, I'm also given that the rate that the volume is changing, dV dt, is equal to 2 meters cubed per minute. I'm given that information there. And this is positive since my volume is increasing. As time increases, more and more water is flowing into the tank. That's why I have a positive 2 there, okay? And my radius r is fixed at 2.5 meters at that instant. Now, number 3 says form an equation about how all these variables are related. Okay, my equation for volume of a cone, you can go look it up in the reference table in a Blackboard that I've got posted, or you can just go Google the volume formula. And that formula is 1/3 pi r squared times h. Okay, we've got ourselves a little situation here. I have r and I have h. If I start trying to take the derivative with respect to time of h, I can do that implicitly, but something that you'll notice is I have a value for the derivative dv dt. I'm looking for dr dt, but I don't see anywhere that gives me a dh dt number. Okay, so I don't have anything that tells me dh dt, so I need to figure out a way to rewrite dh dt in terms of, or I need to figure out a way to rewrite h in terms of r. That way I can avoid dealing with dh dt. So I need to come up with a formula. It just so happens this is a very common principle in related rates. It's similar triangles, okay? And so what do I mean by similar triangles? Say I have a triangle. Let me try this again. So I've got a triangle with side R and H, and then a similar triangle would be a triangle inside that triangle. And so maybe this side here, this is, this is 2, a little bit smaller, right? Maybe this is like, I don't know, 2 and 3 here. Okay, so how do similar triangles work? How would this relate to this larger triangle here? Well, if I take the ratio of this side divided by that side, then that would be equal to the ratio of this side divided by that side, 3 divided by 2 there, okay? So I know that those numbers aren't correct. You know, you don't have to say, hey, Mr. Clark, you should probably switch those around. Don't worry about the numbers. It's more about the ratios that you're getting correct, okay? So this R divided by H here is the same as this 4 divided by 16 here, okay? So I'm using that equality here. And so what I can do is I can cross multiply 4 times H and R times 16. Those are equal to each other. And if I solve for H here, I divide both sides by 4, then that becomes 4R. And I can replace H with 4R into my equation here. And if I multiply this out, I have 1/3 times pi, which is pi over 3. And then I have multiplied by 4R cubed. And so I get this formula right here, which might look familiar to you. Maybe you have that in your formula chart already. Area or volume for a cone is 4 pi cubed, or 4 pi divided by 3 times r cubed. Now, number 4 says take the derivative with respect to time. So the derivative of v is dv dt. And then I'm going to pull the constant out front, and I'm going to take the derivative of something cubed, which is 3 times something raised to the 2, multiplied by the derivative of inside. Derivative with respect to t of r is dr dt. So now I'm going to start plugging in, okay? What can I plug in here? Well, maybe not yet. Let's simplify this. These 3's cancel, so I just get 4 pi. Now, number 5, I'm going to plug in everything I know. So dv dt is equal to 2 meters cubed per minute, and r is equal to 2.5 meters, okay? So if I solve for dr dt, that means I'm going to take all of this and divide it into this here. And so what is that? That's like 2 meters cubed over minutes divided by 4 pi times 2.5 meters squared, and then square that 2.5. And so meters squared cancels with meters cubed to just give you meters to the 1 unit. And then 4 and 2 cancel. Yikes. Okay, so that gets me 1 and then multiplied by 2. And I have that pi left over. So after all of that simplifies, I'm going to get 2 over 25 pi meters per minute, which the units make sense here because it's dr dt, how the radius is changing with respect to time and minutes, so it's meters per minute. So interpreting this in the context of the problem here, how fast is the radius changing at the instant that the radius of the tank is 2.5 meters? That's this point right here. The radius is increasing. Why is it increasing? Because the derivative is positive at 2 over 25 pi meters per minute when the radius of the tank is at 2.5 meters. Okay, I'm going to zoom out, that way you can see the whole problem in one picture.